A few minutes. Good evening, everyone. Great. All right. It's great to see everyone. We're going to be starting the meeting very soon, in about 10 seconds. Or actually, it's after. It's already a quarter after, so we should get going. It's very good to see everyone. Welcome to the, what month is this? The April 2024 meeting of the Madison Astronomical Society. Yes, we've been waiting for April 2024 for quite some time, haven't we? Before we get to tonight's guest presentation, we do have some announcements to get through. First of all, coming up next month on the 10th of May, Friday, 7 o'clock at this very place, UW Space Place, we are going to have our annual election for the Madison Astronomical Society Board of Directors. And as of now, we do have all of our current Board of Directors volunteering to maintain their places in the Board of Directors. You're welcome. With the following change, over the last few years, Martin, our observatory director, has had more and more professional obligations. I guess he's a bigwig director over at Columbus Chemical, and often he's traveling between sites and everything.
Well, still manager. The director title comes with extra money, so.
Yeah, still manager. So we'd like to thank Martin, but we especially for all the great help he's given us the last few years. But since then, he's been busier, and we've had the great luck of having Dave Leipart join our board of directors, and he's a very handy fellow, and he has agreed to, starting in May, to observe as observatory director. So thank you to both. And Dave's, over the last 12 months, has put in a lot of hard work out at YRS, and I personally would like to thank him. And other than that, we're going to be keeping everything the same, except Dave and Martin are going to be switching positions as observatory director and an at-large board member. But of course, if anyone has technical issues that they're worried about with telescopes and cameras and things like that, Martin's a great guy to go to, and he's more or less going to be helping out along the same lines, just as often as he can. So thanks, Martin. So that'll be coming up on May 10th. Now, also, that is the slate of candidates. Again, I'll read it off. Here's the slate of candidates that has been nominated so far. Myself, Lawrence Moore, as president. Vice president, Kevin Santoulis. Treasurer, Jürgen Patau. Secretary, Dan Hislop. Observatory director, Dave Leipart. At-large member, Jack Fitzmeyer. And at-large member, Martin Mika. And also, we'd like to remind anyone that up to the night of the election, on May 10th, volunteers can let us know if they want to stand in for election for a particular position, and those nominations can be accepted up to the night of the meeting. So, but as of now, all the board member positions are running uncontested. Does anybody have any questions? Yes, Kevin?
Yeah, I just wanted to just acknowledge and thank Lawrence for volunteering to run for another term of president, because you don't know the stuff this guy goes through, herding cats through 3.5-hour board meetings and dealing with all the idiosyncrasies on the board right now, and also shepherding us through one of the largest purchases we've ever made as an organization with the renovations down at YRS, security problems we've had, and a lot of other things that have gone through this year. So I want to thank you, Lawrence, for the job you've been doing.
You're welcome. It's my pleasure, because this is such a great community, and this board of directors is a great, fun bunch of people to work with. So I thank each and every one of them and all the people that we've worked with the last few years. It's just been a pleasure for us all. So thank you so much. In line with the security issues that Kevin alluded to, back at the time that happened at YRS, it occurred to us it might be simpler, and for various reasons too. We had one of our members that was like saying, I don't want to, I can't quite, I can't quite stick with being on the board of directors, and things like that. And we had a conversation about all the things that were part of the membership as far as the regular and observing members go. If you're a regular member, you're allowed to use the site according to the observatory rules, but you don't have, as stated in the bylaws, only observing members have access to the buildings and the telescopes that we have. And at the time, we didn't have that many telescopes, and we didn't have that many buildings that were fully functional. So it really kind of occurred to us, dovetailing into an announcement that was just made last night, that we really might want to consolidate the regular and observing members into a single tier at in the middle price, in line with the national, some other clubs that I think we looked up, like a Texas club, and we also have one of our board members is also an at-large member of the Milwaukee club. So what we were thinking, and this is tentative and this requires approval by the general membership, we were thinking of combining the regular and observing members into a single tier for $60 a year. And then all regular, instead of having regular members with not quite as much rights as the observing members, we'd like to pull everybody into, being able to use the site and being able to learn how to use any of the telescopes and be able to use the clubhouse and any of the buildings out there. And this would also include a similar merging for the student levels. We have a $5 student level and a a student observing level at $45, and we'd just like to combine both of those into $30 a year. Since we have so many people here, I would like to start a conversation if people have any comments or concerns about this proposal.
I like it. Good idea. Yeah, I've been an observing member most of my time. I think I'm only a regular member now, but I would happily pay a little bit more to get the observing privileges back. So I actually like the idea.
All right, thank you. Yes, Wayne?
I'm an observing member, so I'm a little biased, but if the regular members don't object, I think it's a great idea. I think, well, seriously, because the more people we can get out there using the facility and using the scopes and joining the community of those of us who hang there, the better it will be for everybody.
And I remember when this topic first came up at the board a couple of years ago, Chris was a member, and I'm interested to know, Chris, if you had any thoughts? Because you've been a long time.
I've been a member for 20 plus years, I think. Yeah, I think it's a good idea on a lot of levels. I would like to see more people out there, especially now that we have those new pads, which are wonderful. Mm-hmm. And we've put a lot of effort, Dave has put a lot of effort into clearing brush and stuff so we can plant trees to block the light. Yeah, it would be nice that if everybody could just come out and use it.
Oh, yes, Kevin.
Yeah, I would just say for someone that rarely uses the facility, because I happen to live very close to it, so I have dark skies in my own yard, I would gladly pay the observing membership, and I do pay the observing membership just to support this organization, because we've been doing so many good things and we're getting so much recognition. I just like to say that even if you can't be using the facility or you're too far away from the facility, it's still a good idea to support the society.
Yes.
So I think this is a great idea. I've been a member, observing member for last 4 or 5 years, and I started off as an observing member. And really it will attract more people to the society and help actually grow the outreach and grow the hobby and grow the science. So this is absolutely great idea. And when I've spoken with some of my friends who are not members, they would like to actually come in and use the telescope and use the facility and get into the hobby. So this is great, and it keeps the membership simple. Having worked in other charitable organizations, you don't have to think about, should I be an observing member? What are the benefits? What are the not, so it really keeps it very simple. So thank you for doing that.
You're welcome, and now I kind of refreshed my memory, but when we had the security issue a couple of years ago, it was a kind of a logistical problem distributing the new passcode to the clubhouse to all the members, and it was like, are we sure that this is an observing member? Are we sure that's a regular member? And then it's going to simplify all that. Yeah, oh, yes, Chris?
I've talked with people, like I told a friend that I was going out there. I went out Tuesday night, and I was out at YRS all by myself, and I told this friend who's a man and a member, he's like, aren't you afraid to be out there alone? And I'm a country girl, and I'm not. But I think if we have more people using the site, that goes away.
Yeah.
If you go out there that there will be one or two other people out there, that solves some of the security.
Now, occasionally when I'm out there, I do hear raccoons fighting, and that startles me sometimes, but coyotes.
If the raccoons are too close, I'm in my car.
Yeah. Yes, Jurgen, I'll be right with you.
I just want to say that the 14 pads that we have out there, I think with their use, maybe 5 or 6 of them are used when people are out there. There's a lot of capacity out there. And second of all, we've also started relatively recently doing a lot more outreach out there. Lawrence has started the monthly star parties, and we're hoping that a number of people, or maybe everybody, who's simply a regular member will take advantage of that and come out and see what the hobby really is like. Because I think a fair number of people who are just regular members join because they're interested in astronomy. But let's try to hook them also in going out and doing some observing, just visual observing. Plus, we are starting to get equipment that is actually usable by people, rather than being in various pieces where you have to kind of put them together like a big puzzle. So we hope you all enjoy it. All of you regular members.
Yeah, we have the 16-inch Star Master. We just added a 14-inch Dobsonian. We have an 8-inch Dobsonian, and we're also just recently acquired a C-Star for anyone who has a smartphone or tab and they want to do some deep sky observing. Yes, Frank?
I strongly support this new idea. It makes no sense in an organization like this for any of the members to have any impediment for full participation. It makes no sense at all.
Absolutely agreed. Thank you so much, Frank. Yes, go ahead, Dan.
So for those of you who don't know me, I'm the secretary, Dan Hislop. I'm the one who sent out the email last night, and I've been the one. Oh, you don't need to clap for that. But this has been kind of, I'd say, fair to say, my baby. I've been wanting to do this for a long time. But part of that, too, is I also want to hear the dissent. You can all tell from just tonight that the response to this so far has been overwhelmingly positive. But we're all fallible. There might be oversights. There might be, some long tail that we're not seeing. And especially when all the feedback is overwhelmingly positive, if someone does have a criticism or a concern, sometimes that makes it even more difficult to tell us about it, because nobody wants to raise their hand and say nay. So if anyone out there in the group here or online is seeing this proposal and thinking, I'm not sure about that, absolutely please send me an email, send the board an email. You can just shoot an email. If you don't have my email address, the info address that's on their website comes to me. I want to hear from you.
Yeah, because, if somebody brings up a concern, there may be a way to address it, and we'll make every effort to address the concern. Oh, yes.
Yeah, hi, Kathy Purkowski. Just a question about how good is the parking out there? Because when we've been out there, sometimes in the winter, obviously we aren't looking at winter now, but how's the parking going to be, especially if it's soggy? Is there enough room for everybody in the club to park there?
Yeah, I think so, because, there's, we lost a little bit of our parking closer to the clubhouse. However, we did clear some area south of the arborvitae trees. Our neighbor, Carson Yana, whose grandfather donated the land originally, has said to us multiple times, you know, on the other side of the lot line in that field area, if people need to park there, he's more than happy to let people park there, and he's been keeping that area trim. So, yeah, there's going to be ways for us to address that.
And that's southwest, so you would come in down the drive and park on southwest of our corridor?
Yeah, because you're right. Yeah, to the west of the, where there's kind of a small, not very tall shrub line,
Okay.
on the west side of the clubhouse there. Yes, Jurgen?
I may have missed this. If you did, then I'm repeating you. But the reason we had a two-tiered system is buried in history. At one point, the club was made up of a whole bunch of people, and it was actually very difficult to observe. So the extra $40 that was on for the observing fee was actually designed to help maintain YRS. But that's gotten blurred over the years, and it doesn't make any sense at all to keep that differentiation. Everybody is already welcome to go out there. Everybody should, well, frankly, pay to go out there.
And just to let everyone know, about the only thing we have to do is we'd have to amend the bylaws so that now that there will be a single tier with all of the privileges of that tier explained clearly, and the same for the student levels too. All right, we're at 7:30. Is there any more discussion on that? Oh yes, hang on. Who?
I just wanted to ask, are we going to propose a vote in next month's meeting?
Well, I don't think we need to make a proposal, but we'll announce before next month's meeting that we could potentially, vote on amending the bylaws during the formal meeting next month. It's just a matter of somebody making a motion and then somebody seconding, and we'll have to distribute how we want the new bylaws to read, or we could just clearly explain that we're going to replace the tiers, the language explaining the tiers with this new language, and then so that everybody can see what we're going to have in there. Yes, Dave?
Just a quick mention of the new grounds committee.
Oh, hang on. Yeah, I'll get through all the announcements as I can. All right. So, yes, that is actually the next thing on the list. Is I want to quickly announce that yes, we do have a new groundskeeping committee for Yana Research Station, and I just wanted to let Chris said she had some news about the shrubs.
Hi, I'm Chris Zeltner. For those of you who are new and don't know me, I've been in the club about 20 years, and I am the grounds committee. I'm willing to take volunteers to help. We have 60 trees coming in the week of the 22nd. So in a week and a half, we'll have 60 trees that need to be planted. Dave here has very nicely put in a lot of labor and cleared a lot of area around the brush around the observing area, so we would just need to go in and plant them and water them. And I'm just kind of hoping I can give a heads up and hope that there will be a few of you who would be willing to come out for what would probably be about a half day of work to plant trees.
What is the purpose of these trees?
Block light, to grow up and block light from the road.
Right, okay.
From the road, yeah. This would cover the north and the east.
Oh, what kind of trees and how?
They're, what kind?
White spruce?
White spruce. And we got the biggest bare root that we could get. So most of them will be 2 feet, and then I think some of them will be 18 inches.
What day is this again?
Oh.
We don't have a,
We don't, yeah.
we don't have a day yet.
But yeah, keep your ears to the ground, and yeah, because we're going to be looking for volunteers.
Yeah, it'll be fairly soon after they come, so probably the end of the month, maybe the last Saturday.
All right, yeah, stay tuned for further details. And to quickly wrap up, the next monthly star party will be on Saturday, May 4th. I will not be there because hopefully I'll be with Girl Scouts doing an outreach activity, but Saturday, May 4th at 7:30 p.m. And I think I might have, and the next monthly meeting will be on Friday, May 10th. In addition to the annual election, we'll be having MES member Brian Champion giving us a demonstration on how he built an observatory in his backyard. And he's got he's got, if you've seen any of his photos on the Facebook, he's got a very good operation going on there. And he also has a background as a manufacturing engineer for a small local company. And so he's got some really interesting advice on how he cheaply designed his own building and put it up. So join us on Friday, May 10th for that presentation. And now it is, almost 35 minutes after the hour. So for tonight's presentation, I would like to present the Planetarium Director at the Madison Metropolitan School District. Ben Senson is here, and he's giving us a presentation about how whether or not they were able to reproduce the Eddington experiment. For those of us who are big fans of general relativity and Einstein's theories, they did this experiment with a total solar eclipse to prove his general relativity theory.
We're all in big trouble if this didn't work.
Yeah, if it didn't work, we're toast. And just to tell you a little bit about Ben, he's the Planetarium Director for the Madison Metropolitan School District. He's been an educator for more than 30 years at the Madison Metropolitan School District as a classroom teacher of the earth sciences, physics, aerospace engineering, and astronomy. At Madison College, he is also a senior part-time instructor for physics and astronomy. And on behalf of all of us who has benefited from public schools and science teaching in public schools, let us welcome and thank our presenter tonight, Ben.
Thank you. Thank you. Hi, I am Ben, and it's been 4 days since my last eclipse. But I do know when I'm getting my next fix, so I'll be okay.
And I almost forgot. I'm sorry to interrupt you. After the meeting, for those of you who would like to get together for a photo, if you traveled somewhere to see an eclipse and are wearing a T-shirt, well, after the presentation, we'll get together for a photo. And also, if you would like, Ben, people would like to ask questions, just raise your hand.
Anytime.
And I'll come with you and let you talk through the microphone so people online can listen to your questions. So thank you very much, Ben. Go ahead.
Thank you, thank you. So I do have to ask, how many of you know we have a planetarium here in town? Beautiful. Do you know we have another planetarium in town? Aha, there are two. One is on the top of Sterling Hall. It's associated with UW-Madison. It's used mainly for teaching undergrads the current sky and motions in the sky. I'm at the other one, and it is brand new, just built in the 1960s. And my biggest challenge I took over about a year and a half ago. This will be my second academic year where it's my daytime job. And my biggest challenge is every public show, I always start with, so who's never been here before, just quick show of hands. And it is still about a third to half who didn't even know we had a planetarium. And I give them the same joke. Well, we're brand new. It's only been since 1966. So in the last couple of years, I've been trying to make it as approachable, kind of like you do with your facility and the observing site, make it as welcoming to anybody who wants to come in. We've added programming on First Nations star knowledge. We have Pink Floyd. Okay, that's been a very, very popular show this spring, and it's going to continue into the fall. We are closed for the summer. We're bringing in a program called Mesmerica, which is a very different kind of audience from my normal audience. And we've gone from supporting about 15 to 16,000 students per year to the last year before I took over to a new record this year of over 29,000 people served. Wow. Yeah. So if you've never been, shame on you. We would love to have the MAS crowd and all your friends, family, etc. Come and join us at the planetarium. We do a monthly public show that is always thematic. This month it is going to be on Mars, the Ultimate Voyage. So a planetarium program developed by my friends up at the Bell Museum, all about how dangerous it is to travel through space to some place like Mars, and then how we figured out that stuff and made it safe. Okay, so it's a wonderful program. Come and join us. Hopefully you can be there for that. Tonight I am here mainly because I got roped into this extremely weird, bizarre experience. And I mean that honestly. It was January where I attended the AAS meeting. You know where the next one is, right? Yep. Summer meeting right here. So if you've never gone to a AAS meeting, you can get a guest access and things like that. But I went at a AAS meeting and I went to this social for educators and I was schmoozing. And this guy started talking about this weird, bizarre stuff. And I'm like, that's me. And we just kept chatting, and I'm like, I want in. So I want to assume that maybe not everyone knows exactly what the Eddington experiment is or what's behind it. And so as an educator, I'm just going to start at kind of ground zero and go from there. This is the universe, at least in the time of Newton. So his understanding of space and time was that space and time were fixed quantities. And if you threw something into that, like a star, I kind of recognize that one, then it really made no difference to space or time. And the way that things interacted in space was through this amazing thing called gravitation. But it took two to tango, literally. You needed two different masses, and then they would interact. And how instantaneous could that be? How would that propagate? How was the force carried? This was a huge question mark that stayed in science for a very long time. Well, in the Einsteinian reinvention of the universe, he basically said space and time are one thing, and they are not fixed. They are not a fixed quantity. They can actually be modified by, certainly, the presence of mass. And in this graphic, that's all it's really showing is the rippling of space-time as a mass is moving through three-dimensional and fourth-dimensional with time-space. Now, this is greatly exaggerated, okay? So, go Kip Thorne, go LIGO, go gravitational wave observatories. Showing a graph like this makes it like, what took them so long, right? All right, we're talking about a wobbling of the space-time on the order of the size of a fraction of a proton. And so to detect that is an amazing invention of technology and persistence to work all the bugs out. And now that we're going through the upgrades to these facilities, it's going to inform us to a whole other degree of accuracy and precision, exactly how the universe works. So the Einsteinian universe has some bizarre outcomes. One of those is you can eat space-time. I don't know if you ever thought of it that way, but black holes can literally pull in space-time. That is why there is a physical limit to the speed at which you could possibly climb out. And since you can't go faster than the speed of light, nothing can escape from that event horizon. It's literally you are swimming in a river, and the river is space-time being ingested. That's one way to think about a black hole. And so how fast can you swim in a river? Not as fast as I used to, right? So another outcome of this, and this is a wonderful little book that a friend of mine, the dude I met at AAS, sent a nice image because I said, you got to send that to me. But this is a little pamphlet that talks about this little thing called relativity. And in there, a dude, I'm not sure if you've ever heard of him. I call him Al. But Einstein wrote a little proposition. By the time he gets to the end, and I know you won't be able to see this, but by the time he gets to the end, in his last paragraph, he says, okay, now put all that weird mathy conceptual argumentation stuff together, and this is the gist. I think one of the things that you should be able to see is that because light does travel straight through space-time, if space-time is Euclidean, what happens if we warp space-time? Well, then a straight line path is no longer a straight line, and therefore stars and masses should deflect the path of light as they pass by the sun, and no one is ever going to notice it because what's our observing challenge? Yeah, you are a solar observer in the daytime or you're not, right? I mean, if you're looking anywhere near the sun, you're like, do I really want to take my brand new camera and accidentally image the sun without a filter? Right? You either do dark sky stuff or you do the sun. You don't do both. So interestingly enough, he says, as the fixed stars in the parts of the sky near the sun are visible during total eclipses, see why I'm doing this right now? It's been 4 days since my last eclipse. Near the sun, the consequences of this theory will be comparable with experience. You can image close enough to the sun. And it would be most desirable, he's very gentle on this, if astronomers would take up the question here raised. What I love is the next sentence where he basically says, I don't even know if you guys have your act together that you have the technology to even do this, okay? I've got my wackadoo theory, and theory doesn't need you practical people. But if you ever get there, use your telescopes and see what you can observe. Okay, so the modern Eddington experiment is in a couple versions. The current version is called 2024 because, of course, we have an eclipse going on right now. And I do want to point out that this is not really questioning Einsteinian general relativistic understandings of the universe. It's been well established by many lines of evidence. But the first nail in the coffin that got everyone going, wow, holy cow, just like, I don't know, discovering a planet with Newtonian gravitation, it got people's attention, was this Eddington experiment. So what we're really doing is using modern, advanced amateur grade equipment, basically, to replicate it with greater precision and greater accuracy, which in science is called validity. If you actually express your answer and how crappy it is, that's science. If you leave off the how crappy it is, it's an opinion, right? You got to know how bad your equipment is. So that's really what we did. And once again, greatly exaggerated. So during totality, what you'd have to do is say, well, I know where the star is supposed to be, and then what I should be able to measure is the actual deflection of it from its known location. Now, historically, this is a huge problem, and it was first attempted to be solved actually before May 29th of 1919. You guys know how eclipses work. What are the odds? Yeah, you know exactly what I mean. No matter how well you plan, as Mark Twain said, climate is what you expect. Weather is what you get, right? And so it's not till 1919 that people with the right equipment in the right place could get to a major eclipse. There's actually a little hiccup of going into a war zone and trying to get out, and they keep your telescope, things like that. So certain people could not get to other events. Even 1919, only 2 real groups were doing serious investigating because of a lack of equipment. Their stuff was still in lockdown, mainly in Russia. So there's 2 groups. One group went to Sobral, just off the coast of Brazil, and the other one is on the east side of the ocean on a little island called Principe. And this is, of course, the Dyson, Eddington, Davidson group over there. In Sobral, let's just leave it as it didn't work out. Like I said, you know eclipses. All kinds of things go wonky. You don't get enough data. It's not high enough quality. You aren't really proving anything, right? So sometimes the instrument really does matter. By the way, this is an amazing setup and a really interesting way to do it. Don't move your scope. It's so big. We'll just move a mirror, right? That sounds like a lot easier. So what did Eddington actually wind up with? It's not a perfect experiment, but by the time you're done, they wind up with this is probably the most famous of the images that came out of it. And what you're looking at here is everywhere you see the little white lines on both sides. And so my understanding is they can't see that at home, so we'll play nice with our little mouse. So everywhere you see these little dashy lines right here is a star that was bright enough that they could convince themselves it was a star. Now, this is 1919. You can't tell your computer to boost the contrast and play with the histogram, right? I mean, you basically had to go in there and just look closer and closer and closer. I mean, you could use some photographic techniques, but this is glass plate technology. And so once the plate is developed, the plate is the plate. And after that, you're just like, I don't know, what do you think? What do you think? Well, I don't like him, so I'm not going to try. Yeah, I go with you. I mean, it's really like an opinion almost, what are stars and what are not. And so when you put it all together, there's really only about 7 stars that are of high quality. They have a significant enough contrast that you're like, I can figure out where they are. Remember, the whole goal here is, where is it supposed to be? Where is it going to be? And so if you don't have confidence that you know where they are, it's a wash. So they got this, and of course the articles got put out there, and it's pushed out into the world as we have answered the question. It looks like the universe is an Einsteinian universe. Now, between the time of the Einstein article and this, he actually doubled his estimate of how much deflection you're going to get. And it's a huge quantity, 5/10,000ths of a degree. Woo! Thank God, right? Something easy to measure. And this is what actually gets published, and it's called the Eddington experiment, but I do want to recognize the people who did the work here. This is Dyson, Eddington, and Davidson are the 3 major astronomers who are in the published paper. Fast forward a little bit. You all know this map. Like I said, I came into this in January. I am the Klingon, and I don't mean that in the Star Trek sense, but I am the person who got in at the last minute and just happens to have equipment that is pretty well suited to doing this. And I learned as fast and furiously as I could in the last 3 months from some amazing people who gave this a whirl in 2017 just to see if it was even technically feasible and worked out some of the bugs. Then especially over the last year, so I said January, a year is longer than that, worked out most of the bugs over the last year, with me jumping in the last 3 months. But this opportunity in 2024 is huge because for the first time, our goal was to get 15 telescopes with equipment that is fairly comparable or at least is well suited to the experiment, all operating at the same time. And that's huge. Rather than having one setup, one place, totally at the whim of nature, getting 15 scopes at 2 different sites is really what the modern Eddington experiment was all about. The people I definitely have to give props to is everyone who's listed, and the 3 who are photographed are the ones I know had a ton to do with it based on my 3 months of experience with the group. I am sure I'm leaving one or two of these other people in the bottom of the list who did a lot more than I know of, but they just didn't do it in the 3 months. So I don't know. But Don Bruns is a AAS recognized Chambliss Award winner for amateur donations or contributions to the art of astronomy. And he was the one in 2017 who kind of went out and got this thing working. Toby Dietrich is the person I ran into at the AAS meeting. And he is a cheerleader like you would not believe for, there's got to get people doing this. Every undergrad should be doing an Eddington experiment. You're like, are you wackadoo? Really? You need an eclipse, you know, right? I mean, so, all right, not everyone. And then we have Richard Berry, who I think everyone has known. He's labeled technically as an amateur astronomer, but if you've been around, Richard's been publishing and writing articles for years and years and years, and he was supposed to be at my observing site in Texas, but some issues kept him away. That's me. I get a big photo and my rig because I'm talking. So there you go. So what was supposed to happen? This is that eclipse sky, right? Significantly different than usual. Things are showing through it. I hope you all got the totality. For those of you who didn't, hopefully you get to Spain or Australia or South America, or sorry, Antarctica in the next couple of years. Harder and harder to travel to them than this one. But Jupiter and Venus and Saturn and Mars were supposed to be visible, and Jupiter and Venus in particular were very, very easy. All right, you see a problem. 5/10,000ths of a degree. This is the sky you need to do that, right? You got to be able to see stars. And in the time of Eddington, they actually had to see these stars and know where they were, and that meant the sun couldn't be there if you wanted a photo of where they're supposed to be. So how do you get a photo of the same patch of the sky under similar sky conditions with the same angle of observing, so you get the same refraction and everything? How do you know where the stars are supposed to be pre-Gaia? I mean, we have such a wonderful advantage, right? They had to stay there for 6 months. And you could choose 6 months in advance and take nighttime photos of that patch of the sky where you know it's going to occur. Thank God for math, we can predict it. Or stay for 6 months after. The preference would be before, because that way as soon as you get your data, you can analyze it and beat the other guys by almost 6 months. But this is the sky you need. Now, this is my setup. I went running across the United States. I tried to catch it early, and like I said, Mark Twain, climate is what you expect, weather is what you get. I came in it so late I was not going to work out trying to ship technology across the border and getting permits and stuff like that. So I went as far southwest as I could. This is Leakey, Texas. And so Leakey, Texas is sitting right here. It's northwest of San Antonio. That's about 30 miles north of Uvalde, which sadly everyone knows where that is now, roughly. But that's where I was going to be, and with about 7 other people, including Richard. And then down in Mexico, near Mazatlan, in a little town basically called Durango, an actual town called El Salto, Mexico, the other 7 people were going to get set up. And the advantage of that is, if you've ever been to that part of Mexico, they don't have water, right? I mean, the odds of clouds and things like that was significantly less. And so the climate we expected was the farther you go southwest, the better the sky should be. And then, of course, nature happens. So where did I actually observe from? This is Cape Girardeau, Missouri. And if you don't know this, Texas is not next to Missouri. So I was camping on this is a floodplain of a little river, the Rio Frio, going through Leakey, Texas. I stayed there till Sunday morning after driving 2 straight days basically to get there. And Sunday morning at 9 o'clock, I looked at the national weather forecast, and you know what they were predicting? Yeah, 99 to 100% cloud cover, thick. It's going to just be a total wash. Looked like most of the state of Texas. Now, it didn't turn out to be quite that bad, but I was right in the bullseye of the dark. So I'm like, this is going to suck. And I'm going to just bug out. I packed everything. I went in a Prius. Okay, if you want to see the photos of how much crap I packed in, look at the State Journal. Oh my God. And so I bugged out and I traveled. This is what we were going to have, was over 4 minutes of totality, which is a very, very long, totality, which is great. Not anywhere near the theoretical limit, but pretty darn good. That works out to be a nice time of day too. If you do the correction from UT, you take 5 off that. It's going to be about 13-ish, so that's about 1 in the afternoon to 2 in the afternoon. This is going to be beautiful. This is a great time to do this. That is the challenge, by the way, of Spain. It's going to be very late in the day, very low in the western sky. So, and if you know this, they got mountains. So you can't be in a valley, and that's a lot of the mountains is the valleys. So, got to work that one out. This is the standard equipment that most of the people were using. So very nice stuff. Teleview. I think you probably heard that name maybe at some point in your career. For me, I have a Stellar View 102T. And so you'll notice, yeah, go Stellar View. Okay. All right, there we go. It's a very, very nice optics. I love the thing. It's about a 4-inch aperture. You notice they're down maybe closer to a 3-inch, and they were going to stop that down anyways by putting an aperture on it. We can talk about that if you really want to. But I had a focal reducer, and so did they, bringing it down to get an effective focal length somewhere around 500 millimeters. So these are fairly fast, fairly wide field of view. On purpose, you got to catch enough stars you can do the math on them, right? So you can't just catch one, or you can't tell where it is compared to anybody else, right? You got to see deflection from an address. How do you know the address? You need a whole bunch of houses, streets. You got to make a grid, right? For an image sensor, almost, I'd say 80% of the other observing sites were using the ASI 2600 or the 1600. For me, I was using the ASI 183 GT, which is high resolution, great quantum efficiency, very small pixels, and so if nothing else, I should have had like really good details, right? All right, now back up. I am not an imager. I have really good equipment. And then I am really not an imager because I don't have the time to actually stay up and go out. If you've ever worked in public schools, much less a planetarium, with evening program, I love my equipment, but I'm not an imager. I just like to collect good stuff. All right, with that said, on average, kind of between the groups, this is the math for the TeleView and the 2600, this is roughly the field of view we're talking about. And you know, everyone goes to the eclipse to get this visceral experience of the god of night stealing your sun and freaking your brain out that, you know, the sun just disappeared in the daytime. But for us, we actually needed the sun as the anchor because it turns out that that 5/10,000ths, yeah, that's the high end of what you're going to notice. Everything else is smaller than that. And as you might imagine, if it's a warping of space-time due to mass, it's a radial phenomena. So there's kind of a forbidden zone where nobody in their right mind goes anywhere near it with kind of old school optical, you know, photographic equipment. It's just too many things can go sideways. The depth of the exposure you need to see these stars, I mean, you're just going to blast out everything. With modern equipment, we're not taking long exposures. We're taking extremely short exposures so we don't fry anything out, and we're dumping all that data as fast as we can to clear off the imager, and then going back to get another scoop. And another scoop, and another scoop. So CMOS detectors have changed everything, basically. And you'll notice we have an east field and a west field. You want some redundancy. If it works over here but doesn't over there, you know, you got, once again, crap for data, right? And so you got to do a double check with the same equipment, with the same camera, with the same everything. So we did an east and a west field. And then this is the do not enter zone. So why is it that we're in 2024 and we're like, yeah, somebody should do this? There's been about 7 other attempts, and the error bars are all over the place. Why is it more than 100 years later? Like I said, nobody wants to get that close to the sun with older equipment. And second, this method of finding these deflections require you to use a method that you won't care about the name. But you need to take some of the eclipse, those precious totality seconds. You have to get calibration images during the eclipse, and preferably of more than one field for the same reason of what if one's wonky. So who is in the right mind is going to take 4 minutes and 24 seconds and give up a minute to a minute and a half of those? You're in next time. All right.
But I was taking Spectra, so I'm foolish.
There you go. All right. Yeah, Spectra is a whole other challenge. So this is basically the gist. And for us, these calibration fields had to be far enough away. By the way, far enough away is literally like, you know, 2 degrees, but just to be sure, you go like 10. There's no measurable deflection. As soon as the sun's not in the image, basically there's no measurable deflection. That's how sensitive this experiment is. But we got about 10 degrees away, and we even had to preload the work because the idea is in those valuable seconds, you can't be doing things that could be done on any dark night. And so you'll notice that the first thing that's up here is actually zenith calibration frames. Once you have your rig set up, and that was another twist, is who can actually just bolt everything together and then never touch it again. In a perfect world, you can't change anything about your setup because when you're trying to get this fine of a positional measurement, any change to your optics will actually produce just as big of deflections, basically, as what you're trying to measure. And so once you bolt it together, it's got to be left in place. So the idea was, we'll do this in advance. Why was I in Texas on Friday? I don't know. I don't like living on rocky riverbeds on a floodplain. Big flash flood down there. But the idea was every night, when it got dark, you could just point straight up, move a little bit, to do all this stuff to get the equipment sort of numerically represented in the software. And then on the actual eclipse day, now the clock is ticking. Now you got to get an east field, a west field, and 2 calibration frames, 1 on each side. And so notice we're very compressed time frame here. You only are getting about 2 minutes of data, but you've saved having to do all of this in advance. So this was the observing plan. You know, so we got some bright stars in the background. And anybody know that one? We were in Pisces this time. And so the double overlapping of the science fields, once again, overlapping. So you know that this field lines up with that field. And anything that you see in there, you can do that with. So 2 overlapping. And then this is all the farther you had to go to get a calibration field. So to be efficient, the idea was, let's get at least 1 calibration field. I mean, if everything else goes wonky, you got something you can process the data with. Then you slew to an actual science field and try to make sure you get like the deflection data. And then you try to back that up, because that's the really valuable, can only do it during an eclipse thing. And then worst case scenario, you could have gone back 6 months later and done the other 2, right? I mean, you could, it just would suck. So you slew to the other side and try to figure it out. We do not know at this point whether this is the optimal configuration for scanning it. No one's ever done this. So it may be that you'd want to do 4 fields around the middle, and you only really need 1 calibration field. We left it open enough that it was kind of a free-for-all that we discussed for those 3 months. What do you think we should do? But the last thing was, but you do whatever you do. So if you want to do a 4-panel mosaic, go for it. We don't know if that's better or worse. You want to do a slightly longer exposure, shorter? Nobody knows yet. This is all based on just doing the math and trying to see if it works, right? So one of the huge things, I got like I said, there's names on there, and I just don't have really good photos of them at this point. But this is Doug Smith, and his son Andrew is getting his master's in London. These 2 are brilliant science people and coders. They wrote custom software for this endeavor. In the very first page here, I mean, it all looks like just so commercial grade, right? It's actually pretty slick. They encoded an optimized plate solving. So in some ways better than anything else that's out there, because it uses the best little tricks that everyone has published out there and says, why don't you do them all at once, right? So this is a plate solve of the little stars that were detected in a field. So those zenith fields is one of the things you can do with them, is feed it to the system. It'll say, this is where all the stars are, and based on the geometry, I can tell you exactly where those 3 are supposed to be from each other. So I can, if you don't know what plate solving is, it's figuring out how to unwonky, that's a physics term, unwonky your image, right? Put stuff back, or at least know how to put stuff back where it's supposed to be. In order to get the good addresses. Now the next step in the software was, okay, so we got to know, where they are, but that means you know who they are, and if you know who they are, then you can put more information on them. And you can't process every last little twinkle you see. The dimmer they get, the worse the data gets, right? There's more variation, harder to get a centroid. And so these are, you could pick 100, 200, 300. How many bright stars do you want to lop off the top to be the ones that you do the analysis on? And that's literally just a, check the box. I got to remember the viewers at home. You just literally change this number and you can get more or less stars. And once again, we don't know what's optimal. But 200 seemed like a big number. So great, then what? This is the computation that comes out after the fact, after the eclipse is done. And those are all those bright stars, so there's 200 of them. And the thing I would challenge you to think about is, you see that little dot right there? That's 2 symbols. That's 2 symbols. One of them is where's the star supposed to be. And like I said, we have a huge advantage in the modern world. Gaia has been orbiting for years, and they're on what? Data release 3, and it just is a more expanded database, more and more errors are eliminated. We know to tremendous decimal places exactly where every star is supposed to be. That's one of the symbols. The other symbol is, okay, based on your image during the eclipse, here's where it was. I dare you to see the difference. Here's the cool thing about the software. I said, these guys are brilliant coders. They're like, well, yeah, you're never going to see it. Why don't we just let you free-for-all zoom wherever you want? So, oh, we're not quite there yet. Forgot this was in here first. How do you take the optics out of the data analysis chain, the pipeline? Well, you have to characterize the defects, basically. that's in your optics. There's no such thing as a perfect lens, right? You actually know your Strel rating on your telescope? All right. Yeah, so do I. It's really good.
Stellar view.
Yeah, it's a stellar view. They send you the little report right with it. It's awesome. Let's just say I'm really close to 1.0, right? Every optics has defects, though. Doesn't matter, no matter what. This is literally based on looking at the stars from those zenith images yet, so no deflection. This is the computer saying, what is your error in deflection? And if you notice, the optics here are introducing an error in pixels of sub-pixel accuracy. So this is what mathematics can do for you, is you can actually say, this spot in my optics on this pixel, see why you can't move it, down to less than a pixel. I can tell you exactly how off this pixel is at telling you where things are in the real world, in the real sky. Yeah, whew. So when you go through and you process that with the eclipse, now this is where my brain jumped to automatically. I finished this at 6 o'clock tonight, so, okay. So this is what it does with an actual eclipse set of many, many images fed to it. I kind of flashed through it pretty quickly. We were doing about 0.3 seconds, so about 300 milliseconds exposures, as fast as the camera could download them and still keep track of them. And so with CMOS cameras, that means many, many frames per second, which means you're winding up with these folders that have hundreds and hundreds of images in them. They do have to be visually inspected, so nobody was stopping the camera and starting again. You just started the camera, and then you slewed whenever you slewed, and there's smeared out crud in the folder, and you just go, well, that's clearly when it started moving. Let's throw off one more just to make sure. And then it stayed crappy until, oh, that's when it settled down. Give it a couple seconds. Okay, now start taking them. So you have to visually clean it up. And then when you feed the cleaned up images, this software does all the stacking, all the summarization, and this is the one where, gotta remember the folks at home, that is 2 symbols. You can zoom in on the other one, it's just less informative. It's your error bar. But if you zoom all the way in on that one, and you notice the scale, I don't know if you can even read the scale, but that is a difference between supposed to be and actual. And I can't even read that from over here. The catalog, or Gaia, is the blue dot, and the yellow one is the observation. And if you look at these numbers on here, the declination error is out in the 3rd decimal place. It's going from 0.00575 to 0.00600, so 25 10,000ths. And the unit is degrees. So extremely precise in both right ascension and declination. And then, of course, what you can do is map that out over the radial distance, because every star is a different radial position compared to the centroid. And you can actually monitor the Einsteinian correction for this deflection and wind up with a number. And that's the part that I can't tell you anything, because, my gosh, it's going to take us probably 3 months just to process all the data and clean this all up and run it through all the software and filters. And then we'll write the paper, and that's, I don't know if I'll be on that or not. I wouldn't think so. But there'll be a scientific paper published on this as well. El Salto. Eclipses are so easy. Zenith calibration went great. By the way, the most interesting story is probably that one of our team members got robbed on their way down. We don't know if it was police. They kind of acted like it, or it could have been a cartel. I don't know. But there was a very interesting email going, they asked for 1,000 US. I didn't have 1,000 US. I had pesos. I offered them 1,000 of those. All right, you can do the exchange rate. They said no. And they said, how much US do you have? And I don't have any. I converted it all. They searched every bag, every pocket, and took all their cash. They made it to the observing site, okay, and they made it back out, which is all wonderful. But yeah, things happen. You got to pay attention. I don't know which part of the world you want to go to. Those penguins in Antarctica. But anyways, the crew got there. They got a couple nights of great observing. They got zenith calibrations. It was great. On eclipse day, the winds were 35 miles per hour, gusting to 50. They had 4 telescopes literally blow over out of the 7. And they had another one that was producing pretty questionable data. Now, one of the observers actually had multiple scopes, so there's more than 7 scopes there. That is the one that took basically about 4 out of our 16 telescopes. 4 got what looks like right now will be usable data to actually do the math and do the analysis. In Leakey, Texas, where I originally went, they got zenith calibration. They hung out for a couple days, all that good stuff. And then on eclipse day, of all the places in Texas, it was basically clouded out. There's no useful data whatsoever. So I didn't stay in Leakey. I'm so smart. Remember what I did? I booked it. So what did I get? I'm going to Spain, baby. Don't drive 1,000 miles the night before. You got to do things with software and settings and timing and stuff. I have a video of me going, there it is, totality, and you can see me starting the software and then walk right past my solar filter and never remove it from the front of the telescope. The mount had an issue anyways with a setting, and so it really wasn't tracking right. So my data was trash from the beginning. But it was an absolute blast, and in those 3 days that I was sitting around on a riverbed waiting for a flood or something to do, I was playing with software and getting much more comfortable and confident. So I would now say I'm not the 3-monther who was totally confused for most of that. I'm now feeling like if the team keeps going for the future, I definitely would like to be a part of it. And so I don't know if it'll be Iceland or Spain, but I have a new rig that I'm putting together. That is literally a photo in my hallway. Most of this stuff was supposed to show up before I went to Texas. Of course. It showed up yesterday. So I like my ZWO stuff. I find it very, very reliable. These strain wave drives, the #1 advantage is you don't really need a counterweight as long as your rig is small. And they will track like a beast. So very little periodic error. This is the electronic focuser. They have a new generation of that out. This is the 183, but the MM Pro, so a little bit larger and bigger chip. This is a AstroTech 16 millimeter, so very, very small compact optics. This entire thing, like I said, I'm planning on going to Spain. This entire thing is going to be packed in a backpack with a micro tripod and then some stones to hang on it for stability and carbon fiber. And I'm ready to go anywhere on the planet with a backpack. Maybe one for clothes. That's less important. But that's the rig I'm planning on taking to Spain or wherever else I wind up going. So thank you for listening, and I would certainly welcome any questions you have if I can answer them. By the way, there's a photo of me in my Prius, because I don't know if you know this. If they yank your hotel back and they like do weird stuff to you, you do know that Walmart's policy is anybody can camp in the parking lot. That's where I slept, was at a Walmart in Cape Girardeau, because it was the only place I had.
So I was wondering, with that setup that you just got, what are you optimizing for? Are you going to get at least the precision as you had with the previous equipment, just with greater portability?
Basically. So it's one of the conversations that was going on in the last 3 months, because not only were there those people I listed, there's also, some of them are grad students and undergrads, but there's a whole other list of about 20 undergrads. Right? Toby's big mission is, this is doable, right? Any undergrad could figure this out with 6 months of training. Okay, or somebody else writing the software. So he's like, there should be a lab that everyone does. Oh, by the way, I didn't have time to put the slides in there, but the reason he's really convinced of that is, how do you test if you're really ready to go? In a week and a half, there's going to be a full moon. Most amateurs hate the full moon. That's my moment to test. Because the glare around a full moon, if you image right next to the moon, is about 1/10, about 10% of the brightness of the corona. And so it's actually 10 times easier to image stars through moon glare at a full moon than it is to image during a total solar eclipse. And so you can actually go through and prove it. So in our conversations, the AstroTech was on sale, and it just happened to be that people were like, oh, it's really extremely flat. You can't put an eyepiece on it. It is an imager. That's all it's good for, but it is flat. That's wonderful. One less thing to worry about when you're trying to make corrections. That's the problem with flatness, is basically positional, right? So yeah, all this equipment was picked to optimize it. Like I said, I'm one of those people who's like, this is so cool, I'm going to do it, even if I don't have time. So I'm ready to go, and then I'm just going to hope for August 12th in Spain. Maybe I want to rent a really big villa up on a mountaintop with a western view, right? All right, there you go. All right, questions. I said I'd take questions, and I cut you off.
This isn't a question, but, and I know after I begin speaking, you're going to say he's full of BS.
My name's BS.
Not me. You, him, me. In 1971, I was aware of this Eddington experiment, and I was a freshman at Bradley University in Peoria, Illinois. And because I was constructing a large solar instrument as a spectrohelioscope, I had a celestat, I had a 6-inch f15 refractor, I was familiar with 4x5 film imaging, and I went to my physics professor and I said, we should reproduce this experiment. And so with his help, I wrote a grant proposal to the National Science Foundation.
That is awesome.
And I asked them if they would support the idea of us sending a team to the Golduvai Gorge, where Lucas Leakey's facility was right in the path in Africa. And they approved it.
You went and did the experiment? Okay. See, there's eclipses. They love them, but they suck. Okay.
So, equipment went into rush production, and I started building a Newkirk radial gradients filter, the mechanical type, and we were experimenting. And I think it was like 6 months ago, our wonderful president, Richard M. Nixon, cut so severely the National Science Foundation funding
got canceled,
that they sent me a letter saying that I and most of the others were being canceled.
Oh.
So
That
love
equipment
these
sounds about
Republican
ideal for the
presidents.
experiment.
But anyhow, now that you have done your nice presentation there, I'm wondering if I would have fallen flat on my face.
It's an extremely challenging thing. I mean,
Yeah.
even once you have images in your hand, how do you detect 5/10,000ths? And by the way, the maximum deflection is like 1.75 if you get in kind of the forbidden zone. So it's all based on, this is the sun, there's the 1 radii. You obviously can't image in there. But as soon as you get to 1 radii to 1.5, that's where, like the old Eddington experiment, there's no data in there. So they got some dots, and like if you've ever seen real scientific data, it's like, it's all over, like you threw rice at wet rice at a screen, and then they're like, yeah, straight line, see it? Yeah. You're like, all right, I don't know what math you learned, but it's not a straight. So, you know, the rate, when they say, here's the error bar, what they're really saying is my confidence that that line is this line, or in this case, this curve, is that much scatter gives me such an error bar. And so the original Eddington experiment probably has some, I can't remember the number, probably around a 30% error bar on that deflection measurement. And I'm guessing that would have been your big challenge. You would have got an answer, but I don't know what your error bar would be.
They were supposed to take care of that, and I was building the equipment.
Yeah. Who's your professor, by the way?
Pardon?
Who is the professor at Bradley?
I don't remember.
Okay. Okay. There's some few really old retired guys who, okay. Not that you're familiar.
But we do remember who took away the money.
Yeah, we do know who took the money. Those astronomers get the best sequence. Any other questions or curiosities? Anything or planetarium related, education here in town, anything? Yeah.
This might be a stupid question, but when you showed that image of here's where we saw it and here's where it should have been, and you were talking about the deflection between the two, what about the direction of the offset?
So if we go back to that slide here and just go back to it, I literally was purposely picking, whoops, jeekers. I was purposely picking a star that is right about here. I think it's this one. And so the deflection is always radial.
Yes.
Because the warpage of space-time is always on short time frames. Gotta be careful. I don't know how much you people know. On short time frames, it's always completely radial. Over long periods of time, there's something called frame dragging that Einstein predicted too, which is a whole other thing. You need the most precise round objects ever manufactured to measure it and stuff like that.
So, but it was radial.
It was radial. It was radial. Yeah, and if it didn't work out to be, you'd be like, ooh. Yeah. Which, by the way, there's a whole bunch of other graphs that their software could produce. I'm not giving away the secret sauce. This is all based on old cooked data. None of this is new. None of this is from the current eclipse. This is all old stuff, so I'm not giving anything away. Like I said, they're going to publish a scientific paper, but their software can do all kinds of amazing, wonderful analytical things, too, to be like, how many wonky things showed up, and is there anything that's wonky? What's the biggest wonky? You know, if you know science as well, it's the worst measurements in your whole set that define your error bar. It's not the dead-on ones, right? I mean, you could get lucky 20 times, and then that last one was like, whoa! All right, something is wrong with your method or your technique or your equipment, because clearly you can produce that big of an error bar. How do you know you have an error bar? Because you got 20 that look like they're all around here, right? And so that's accuracy, and then precision is the rice thrown at them. Yeah, that's validity. You need both.
For 2026, have you considered Iceland rather than Spain?
I have, although, you know, Texas taught me Mark Twain.
Yeah?
Iceland would probably be great. So my philosophy, because my family loves me, and I'd like them to continue, is we plan it as a trip, and if the whole thing is a scud, we're going to have fun for a week anyways. True. So we did Jackson Hole, Wyoming, spent a whole week out there, went and saw the moose, and all that good stuff. And then there was this great day at the pool, where we just sipped beverages and saw a great thing, right? This was a lot more effort on my part, but for 2026, it's like if we're going to go to Spain, we're going to plan a trip to Spain. And if we get that perfect day, I mean, we'll make a reservation in the right spot, but if it doesn't work out.
Yeah, they don't have paella in Iceland, yeah.
No, and chance of cloud cover in Iceland in August? It's Iceland. Yeah, it's, I mean, it's same with the aurora. Okay, if you're planning the trip anyway, it's like, oh, we'll go for the aurora. Well, if it's 50% cloud cover, they aren't going to be great either.
You're going to have more towards sunset.
I can't remember the exact time, but it's very close to sunset. It's within, I think, 45 minutes of the actual sunset. So if you have any obscuration or blockage to the west, you are not going to see it. So you got to get either on the coast or you got to get up on a mountaintop with a western view off the villa. Doesn't sound too bad to me, right?
Well, it's so close to the horizon, I'd wonder how much turbulence might impact your measurements.
Yeah,
Or
it could
maybe
be,
there's a way to
refraction is
compensate.
something that actually has to be corrected for. To get a sense of exactly how bad it's going to be, depending on where you are, that's the end of the eclipse being visible because the sun sets.
Yeah, turbulence and the refraction of the atmosphere at best.
Yeah, you're looking through a lot of miles of atmosphere. It's refraction is easier to correct for, turbulence is live and dynamic. So that's one of the other advantages of taking many, many hundreds of pictures over many, many instruments is turbulence in a true sense should be random and should cancel out when you stack and you know, do the corrections and stuff.
Asturias might be a little bit better for you than Barcelona.
Exactly. And in that case, Iceland would be much better just based on timing, but cloud cover is much more likely to ruin things than, oh, it's a little low. Right, you can plan on it, it's a little low.
Egypt the next year, August.
Egypt and the whole Mediterranean and down in, that's a part of the world I don't know if I want to visit, so I'm thinking about it.
Gibraltar next
Ooh,
year.
there you go. And then Australia, right?
That would be good.
Yep.
And Antarctica, visit the penguins. See? Bring a parka. Yeah.
Oh, actually, it's just a comment. A little bit, you said, bring up whatever. A
Yeah.
little bit of science and humor about the very beginning where you were talking about general relativity. I don't know how many of you have seen it. My eyes were opened when I saw I'm sure it's on YouTube, just a video which showed as a function of time what the fabric of space did near a mass. It gets sucked into the mass. And the reason why you fall to the Earth is because you're stationary. You're not moving with respect to it. You're just following the space. And the space is essentially getting sucked into anything that has gravity. Now, okay, many, many years ago, I had a very kind of depressing friend who had this magnet on the refrigerator, which said a really depressing thing. But then I repurposed it several years ago because I figured, oh, I got a much better way of viewing this. This is not depressing at all. Here's what the magnet said. There's no such thing as gravity. The whole world sucks.
You just need a long enough time frame, right? You know. I like that.
All right, do we have any more questions for Ben? Well, if not, on behalf of Madison Astronomical Society, and thank you so much for such a great and entertaining presentation. And this is one of the most fascinating, one of my most favorite topics in physics, I guess, is gravity. I'd like to present to you on behalf of, as a token of our esteem and appreciation for your presentation tonight, a Madison Astronomical Society hat.
Thank you.
Thank you very much.
Thank you.
Thank you very much for being a public school teacher here in this great community of Madison.
Thank you. And this is how much I think of you guys. I'm an observing member, and I've been to the observatory twice. So I take my money every year. Seriously, you guys could go $10 a month. I'd still be in no matter what. So you guys are awesome.
Well,
thank you.
You're welcome, and thank you, Ben. And that concludes this evening's meeting of the Madison Astronomical Society. We'll meet here again on Friday, May 10th. And for those of you who are wearing memento T-shirts from your trips to go see the eclipse, we could gather